let's wait a few minutes. Okay, so let's recall the stuff from last time first. So last time we showed the following here. So let's say you have a function f which is of x, and it is let's say rho matrix, and then okay, so W star is let's say the minimizer of f over some all of x over x. Okay. W is most B. I want to get some guarantee on gradient descent or stochastic gradient descent on minimizing f with respect to the optimum W star. So should I define a gradient descent or stochastic gradient descent? 40 steps, and you have an eta which is b over rho root b. So just to recall what these things were. So the algorithm was the following: we get an update of W for hypothesis W the following way: W2 plus 1 was WP minus eta gradient of F and maybe W0 was 0. And so this was for differentiable functions. For non-differentiable functions, we just used any vector Vt, which lies in the subgradient set of f at for non-differentiable. And just to remind you what subgradient was. So it was anything which satisfies your convexity equation. So subgradient is something. So Vd is V is subgradient of f at W if for all u f of u is at least f of W plus u minus W okay, so pictorially this is just saying that here is my function, here is my point W, then V here is any tangent, anything which lies below this function, and and this line here is okay. So this line here is this line. Yeah, I mean not this line. So this line here. So this here is a linear function of u, as you can see. So for a constant W, for a fixed W, this is a linear function of u, we make just this line. So this equation just says that your function lies entirely above that. So any v which satisfies this let the function line over the line for W is subvariant of function. And if the function is convex, then subvariant always exists, even if it is not differentiable. That's what we will use. Okay, great. The second thing we said is for stochastic gradient descent. So what was that? So so we do not necessarily need to find a single fixed Vt here, which is subgradient. I can even find a distribution so that its expectation is Vt. So all I need is sample Vt from some distribution dt, and this dt depends only on on Wt. Okay. So yes, okay. So sample from some distribution d, and you want that expectation of Vt given Wt. Yeah. So for fixed Wt, I have a Vt now, and that should now lie in the test subgradient. And how can we typically do a sampling like this? So often, like we said, our function here is typically some kind of loss function. So maybe my loss function is summation over examples loss of W for Zi. Where Zi is the ith example. So this is the average empirical loss. So typically you try to minimize some f of this form where L is convex and the shades are perhaps. So here a very fast way to sample a VT like this is to just sample a random example Zi, uniformly at random from 1 to n, and then just compute the gradient of L. So just output gradient of L at Wt. You just do this. Where Zi is chosen uniformly at random. I is uniformly. So that's typically what people do. Great. Okay, so that's what this story was. And indeed, in this equation, you have this parameter eta, which is positive, and this controls how much you move in the direction opposite to the gradient. So we are geometrically speaking, we are moving in the direction of steepest decrease. So I want to decrease my function as fast as possible for a small duration, given the diameter Wt, and that direction will be exactly this. And eta controls how much you move in that direction. And typically, you don't want eta to be too large, because if eta is too large, then the gradient is changing as you move. So maybe this is my Wt, maybe this is my gradient direction. So this direction is gradient of f at Wt. And then if eta is too large, then I might move a lot in this direction. And as I move here, maybe my gradient is also changing. Maybe here my gradient actually points this way, but I'm just moving blindly like this. So moving too large, too far is not good. But you also don't want to move too small, because then you will just take a lot of. So there's some trade-off here. That trade-off is in this. So somewhere, so there's some optimum eta which balances out these two factors. Okay, great. So that's a picture to keep in mind. Okay, so you have run this for these steps, but this eta which you have figured out by balancing these forces, and then you will get that. So compared to this W star, you will have that f of the average W. So average W was, remember, we output the average of the WC. Okay, so if it's average W, then try to find this. Yeah, so that's the best possible, and this is your difference of R. And so this essentially decreases as one over P. So if you make P large, then you can make this as small as well. In particular, if you want it to be epsilon, then P should be like something like 1 over epsilon. So that's what we did last time. So we proved this here. Great. So today I want to do this for in a more general setting. So there are two ways to generalize this. And there's a couple of things to look at here. So question one is what happens for smooth function? This was for Lipschitz. What about for beta smooth? This one. Another question is that what if you want that your W here, whatever you output, also has small r. So notice that here I am comparing against a W which has a small r. But maybe I want my own W to also have a small r. Why do I want that? Because like we discussed earlier, limiting the norm of the W also helps us have a better generalization. So you don't want to have a very large norm W because a small W means that we're talking about a set. The small W means that your problem is now some kind of bounded parameter problem. So if you recall from previous discussions, so convex, Lipschitz, or smooth bounded parameter problem is parallel. Right. So you need these things, and you also need this thing. This we assume, but this is a property of the algorithm that whether we will get bounded parameter or not. So one way to get bounded parameter, if you recall from last class, was to do regularization. So we added a penalty term to keep the double bounded. You could do that. That's also fine. So maybe you want to figure out how to do that. So maybe you want to see how to do regularized. Loss minimization. Right. Using this algorithm. Using STD. So as such, it's not very hard because you just now run this algorithm not on this, but on the regularized version of this. So when F you add a penalty. So this keeps the function convex. So that's good. And in particular, this will also not worsen the smoothness by too much, actually. Okay, we'll talk about that in a bit. So this will remain smooth, actually. It will remain smooth. So starting this will not destroy smoothness. So this remains smooth, and therefore we can still use this machinery, provided we have analyzed it for a better smooth function. So all this can be done. The only thing which is maybe slightly tricky is how to do SGD here. So I could definitely compute the entire gradient and then run this algorithm. That's totally fine. But if I wanted to do it more efficiently, if you want to do it faster, then maybe you want to do a little more work. So earlier we just sampled one I uniformly at random from these examples and yeah, and convert this quantity. Now maybe you want to take a bit more here because the function is now slightly more complicated. Yeah, so that's not very hard, but one has to figure out how to do it. So that's maybe one thing to think about. But maybe you also want to do this directly. So question 3 is that instead of going through this regularization, maybe you want to keep the norm of W small directly in the algorithm itself. So maybe you want to minimize this F subject to a constraint. So maybe you want that your WTs should all have bounded term. So can you also okay, so I want to get the same guarantee, but I also want W bar here to have small. Can I get the same guarantee? For bounded norm of this W bar. Yeah, visible for W bar could have any norm. There's no control. So I want to say guarantee because I'm comparing against W star which is bounded. So I want W bar also to have bounded, and I want the same thing. So yeah, so can I get that? That's an interesting question. Yeah, so okay, so these are things I want to talk about today. That's the plan. Great, so yeah, let's get on with it. So okay, so let's see, which is the easiest of these things. I think this is the easiest. So let's start with this. Question 3 is the simplest actually. Okay, so I want to get this guarantee, but for or not. So let's see how to do that. I'll erase some stuff here. For this picture, you can do that. Okay, so the trick is to add a projection step. So I'm asking the question. So I want to keep the norm of W bar simple. So what I'll do is that I will keep the norm of every WT simple. So I will maintain that each of these WTs has norm. Okay, first of all, if I do this, then it's clear that this has closest norm at most speed. Is it obvious? Why? Yeah. I mean, we could say it's triangle inequality. So if I add up t things, and the order norm at most b, total norm at most p times b. So yeah, so it's enough to maintain this. Okay, so I will now modify the algorithm so that this happens. So how will I do that? So consider the ball centered at the origin of radius p. So here is some ball here, and bracket 2d, and this radius is p. So I want my WT to lie inside this ball. So I'll do something very stupid. If my WT ever goes outside this ball, if it comes, let's say here, I will simply find the closest point inside this ball to this point. So in particular, it is this point. So yeah, so I will just update my WT. That's it. That's all. So often people write this in a bit of a funny way. So people write this as WT plus half as WT minus eta gradient of WT. Okay, so half step is getting this thing here. this thing is W. And then you project here and that's WP. WP is projection of W plus on this point, on the sphere, right? So the sphere of a radius V. So this is a sphere of radius V, centered. So yeah, let's put it on this. So okay, so that's the one. And obviously this maintains this by definition. So the only question is that what happens to the analysis? Because now I'm also updating this. So here is okay, so how it works. It is kind of interesting how the analysis changes. So the key is to argue. So analysis. So here's the key thing to argue. I'm going to show that WT plus 1 minus W star squared minus WT. Remember that this is by how much your distance changes. And if you recall, this was the key difference which arose in our previous calculation. So, okay, let me just remind you of the previous calculation because in case you forgot this. So, the previous calculation we had something of this type. Yeah. So, we had that summation, because what was the previous calculation? This. So, we looked at, so this was somehow the right thing. Where Vt was some subgradient. Oh yeah, or you know, where Vt essentially you're updating, right? So this thing here is Vt. I call it this one Vt. So this is Vt and the separation of Vt. And the Vt. So some Vt here. So the right thing was to look at this. Why was this the right thing? Because remember that we used complexity to argue that we used complexity and some conditional probability argument to argue that so we argued an expectation WT minus W star. Okay. Look at that. Yeah. So look at this in the product. So let's take expectation of this. Expectation. So take the expectation of this. And yeah, let's say this expectation was actually at least expectation this was the key. And what did we remember that I sample V at every step. And we sample a sample of V with some distribution which looks like this, which has this property. So the average of this or the sampling of this in a product here was always at least the difference between f of WT and f of W star. This was the key thing. How had we gotten this? So by complexity, we had shown that so complexity had shown us that f of WT and f of W star was at most some gradient. Yeah, any subgradient like this. this was my complexity. And then we have said, okay, expectation of Vt given V1 through T minus 1 is this subgradient. That was it. Yeah. So okay. So we have first said that okay, I can just look at 1 through T here because after small t, it doesn't matter what happens. This Vt doesn't depend on anything which happens after small t. So I could just do 1 to 3. Then draw this up into this conditional expectation. That okay, first I fix 1 through T minus 1, and then I average out over only Vt. That average after fixing 1 through T minus 1 was exactly this subgradient. That's how we got this. Yeah. So okay, and then we use some adjacent inequality here to compare the average of f over f of WTs versus f of the average of WTs. So that was the other thing. That is kind of how the whole argument. Sorry, people will complain. Jobs. Okay, so yeah, that's how it went, and that's why this is the right thing to do. To understand what happens. So essentially, I have to do something about this one. And how had we performed this? We had used this squares idea. So we had written this inner product as the difference of some squares, and that difference turned out to be something like this. Why was something like this? Because the difference I had something like WT minus so I looked at the square of WT minus theta AT minus W star. So I had something like this. So basically, if I square this up, I will get a term like this. So I'll just combine this with this and take an product with this thing. I get a term like this. And this thing here was our WT equals 1. So that's why we got this. So yeah, just to refresh it. Great. So okay, so now so now how will all this change? So notice that okay, so I still want to argue this inequality. I still want this to be true. But how will I do this now? So it does not make sense to try to expand this directly now, because now there are these two steps. We first do this difference, then we project. So so why indeed we can do this. I will not get this term. I will instead get WT plus half, because that's what this is. So my previous analysis from last time will so that will be kind of upper bounded. Okay, so we had some term here, and the trick was that you could upper bounded W plus half minus W star minus WT minus W star. I just write it down, right? So this is exactly this minus this, and I get some theta term, right? Plus theta Vt square, theta square Vt square. What will I get? Maybe get a half. Maybe get. Okay, yeah. I think I get a barabar theta. Okay, I think I get a barabar theta. Yeah, this is what we do. Yeah, we just rearrange this. Yeah, so this was the thing, and then we had done some telescoping. We had so this was for 1T, it's not for summation. When we sum this up, we cancelled out these things. I mean, you can cancel right now because this is a T plus half. But when it was a 1, we had cancelled these things out. The derivative is kind of the. So now what I want to do is I want to get a t plus 1 instead of half here. So I can do the cancellation. So okay, so how will I do that? So that's what I was going to tell you. That. So the key thing you have to complete this step now. So you want to show that what you really want to be here, this thing here, is only an upper bound on this thing here. It's a lower bound. Hang on, it's a bound. You want to upper bound this side. Yeah, so you want this to be an upper bound. So okay, so let me just write it down. So you want to show that this is at most W2 plus half. This is what I want to show. How will it help you here? By the way, I think I better switch these signs. Is it minus here or do you have minus here? Which way will you get? Okay, so you will get that this thing here is this thing here plus something. Oh no, okay, good. So you get this thing here is something like minus eta this thing here. Okay, yes, okay. So you get the minus on the other side. So you get a you get a minus of this thing. Minus this thing. That's what you get. The other makes sense. Okay, yeah, I think it's correct. Yeah, so you get a minus of this thing. So yeah, so since I want to upper bound this, I now want to to lower bound this, the minus of something, I need to lower bound what's inside. That's what I do. So say that okay, what's inside here is lower bounded by this. And so I can just replace this thing here with this thing. And then everything as goes as before because I can then get the cancellation. So therefore, yeah, from the previous analysis, this is the key thing I have to run here. And then everything is fine. So okay, so now let's think about why this is repeating. This is what I have to prove. Good. Okay, so to do that, we need to understand what happens when you project. So the difference between this and this is that WT plus 1 is a projection of WT plus 1. This is a plus 1. So this thing is a projection of this. So we will understand what happens when you project it. And so here is the key lemma of projection, which is kind of easy to visualize, but I just state it here. So this projection lemma, maybe it is the stress. This is a projection lemma which I want to use. So give me any convex body H. This is some convex body. Perhaps just a sphere. And what's the notation of the book? Just do the same. Okay. So let V be the projection on H of W. So W is this thing, and V is this thing. So the lemma says that for any point u in the convex body, V is closer than H. This is always true. Okay, so first let's see visually, right? Make that obvious. But take a point here. This looks closer than this. Yeah. So okay, so that's the lemma projection. Okay, first let's see why this is useful. You can believe this pictorially. Okay, so why is this useful? Well, the point is that WT plus 1 here is a projection of WT. Sorry, the other. WT plus 1 here is a projection of WT plus half. And W star here, remember, lies inside the convex body because W star is the minimizer of F with bounded parameter. W star is bounded now. W star is somewhere. Yeah, it's inside. So indeed, that's always right. This is at most this, and so it's true. Wait, no, it's just anything. Okay, solved. Cool. Okay, so yeah, I mean, that's the all there is to it. Now you just plug the thing here and so maybe let's just stare at it. So all we said is that okay, so this is my algorithm first. So whenever my norm increases beyond B, I projected it onto the sphere. Is that the algorithm? Why does this work? Well, we just use the old analysis and we just recall this equation for WT minus W star in a product BD. This was the key thing because of this inequality, which we call complexity and conditional expectation. And yeah, and the only thing needed here was these things to cancel. To get the things to cancel, I need this to be lower bounded by this. And why is that true? That is true because of the projection level. It tells me that give me any U inside a convex body. There's always closer to the projection as it is to the point which you had projected. And since W star is inside the sphere, yeah, that's a key thing. Those are inside the sphere. Therefore, this will always be a process. Great. Okay, so this lemma I will not prove today. Yeah, I put tomorrow so like tutorial. Yeah. You can believe this. Okay, so okay, so that answers question number 3. It's maybe not very hard. It's done. Now let's do something else. Now let's do maybe question 1. Start with beta smoothness. I need water. You can take a break. Okay, good. So before I talk about beta smoothness, I want to say a few more words about all of this. So let's recall that for no Lipschitz functions, we are shown that if I do regularized loss minimization, so if I run this any minimization algorithm on a regularized loss, basically if I after adding this lambda non-total square term, then I will get good generalization, right? In particular, I will be able to get back learning. Interestingly, you can also get a guarantee of that type by directly using SGD without going through explicit regularization. So, what does that mean? So, if we consider this algorithm which we had, right? Maybe this algorithm for let's say f is Lipschitz. So you can prove something of the following type. You can show that. Okay, there is a special demo. So here's a theorem. So we show that the SGD output, right? So the W bar, the SGD output. So it's the average of these. Here's my W bar. This satisfies the following interesting guarantee. It satisfies that expectation of loss over distribution of W bar. This expectation here is over my SGD's randomness. Right? In SGD, we sample VT randomly distribution. So yeah, that's our goal. This. So yes, so it's only choice of randomness in here. Okay, in SGD. This expectation is at most the min W in H. Where H is your loss. H is your sphere of radius B. So yeah. Will be of W. Yes. Where epsilon is okay. What epsilon? So your T is chosen in such a way that so T is B square rho square over epsilon. So this is the same guarantee which I inverted. So if you remember from the previous lemma, I had said that this difference minus the optimum for f was at most something like d rho over rho t. So earlier I said that something like f of w minus f of w star equals d rho over. And I was inverted. So again we have this. Yeah, so expectation of f of w bar, which is the output, minus the optimum answer is at most this. Yeah, this. The expectation over the SGD choices. And now, so this for epsilon, then you would get something as a form of b square rho square or epsilon square. This is exactly this thing. But now this guarantee is different. Now I'm not saying that the expectation of f versus the minimum of f. Remember that f here is an empirical loss function. It depends only on the training samples. Whereas this thing here is not an empirical thing. This is the true loss. So I'm now somehow getting a much better guarantee. And that's amazing. So I'm getting this guarantee for free. And so let's see how we get this. The nice thing is that to get this guarantee, you have to just run the HAT algorithm. You do not have to go through the stability analysis of last class. So here we don't have any regularizer. We're just doing this projection. So the analysis from last class was for when you don't project, but you do regularization. So yes, so then you have to go through stability and the calculation. Yeah, but here we're explicitly projecting, and then if you use SGD, then you get this guarantee straight away. Okay, so let's see why you get this. It's quite interesting. Okay, so let's erase this part. You're solid chance. Okay. So, okay. So before I say that, let me just maybe state the algorithm a bit better so that you can appreciate what's going on. Okay. So let me state the algorithm in a different way. So we initialize W1 equal to 0, or W0 equal to 0. And and then at every iteration, so for every iteration, you first just sample, you take a sample, take one sample from a distribution. You sample the same from a distribution. And then you pick some weighty, which is in not as input, just look at loss function. Loss. So what am I doing? I'm saying that I just take one sample from distribution. So maybe I have some samples available with me, I just take one of them. And then at that sample, I look at the loss function, I look at its subgradient. I look at the subgradient of the loss function for this sample with the parameter setting WT. And then I just pick something from the subgradient set. And then I update WT. So that's it. So in essence, this is running SGD with F being your empirical average over your T samples, right? Because how did I write SGD, right? I picked one sample at random and looked at the loss at that sample. So now I'm just saying that okay, let us skip that step and just do it directly. Instead of first writing a loss function which is a sum and then sampling one term from that, let me just sample one instance directly from distribution and look at the loss function there. And this is the same thing, but just write it in a more clear and simple way. So let us do that. And then we just output the average. Output. W bar, which is so that is algorithm. So now Great. So I think yeah, okay. So if we recall the result from the previous thing, right? We had this result, right? Yeah. So so if I just manipulate this, I get that expectation over choices of my VT, P1 through T of W bar at most F of F star plus B rho. And this bound is true for any. This is true for any W star plus Z. This is always good. So find W star with this. Now I take expectation of on both sides. So yeah, so now I take okay, so remember what's F here, right? F here is L ZL. Okay. This is so what is now okay, so now I take expectation on both sides with respect to ZL. So I take expectation over ZL. And this is just the true loss. This is the expectation. Okay, so this is the expected loss over distribution. Right? Does that make sense? So if I take, yeah, so now so that's a fact, right? Obviously. So now I do this. So take expectation over Z and both sides. The constant. So yeah, okay. So this expectation I can switch, and then the inner thing will be that, and then overall we have an expectation over two kinds of randomness in the algorithm, VTs, and randomness in the distribution. I mean, okay, so this particular expectation is okay. I mean, there's no expectation also. There's no expectation here. This is just LD. This is LD. There's no expectation. So if I just switch this here and I get LD, then I get an expectation over the algorithm channels. So overall I get some expectation. This thing is some expectation of LD. So where this expectation is over these the algorithm randomness, which is this is where so okay, the expectation over LD of the output of the algorithm, that's LHS. So that equal. What about this thing? So notice. Okay, so once again, right, by the same logic as before, this thing here is just the loss over distribution of W star. So this is just loss over distribution. What does it tell me? It tells me that the expected loss of my algorithm's output with most the expected loss or distribution of of any W star plus this. That's my goal, right? That's what I'm trying to show. The point was that a guarantee of this type was very easy to exploit using expectation. I could just expectation on both sides and immediately extract a much better guarantee of this. So yeah, so that's a nice thing about SGD. That it allows you to completely sidestep the stability analysis. And yeah, just the simple analysis from last time and today just gets you on this for free. Yeah, so no wonder in practice you see HAT everywhere because of all these nice properties. Okay, great. Okay, so yeah, let's do this. Yes. Okay, one more thing now left is these two things. They are okay. Maybe I'll do the first this one first. Then maybe we'll see this. I know there's time, but at least see this. So it's a bit painful because smoothness is difficult to deal with. But yeah, maybe end of the class so we can push this.
Are there any disadvantages?
Disadvantage. I mean, okay. So see, for convex functions, HDD is great. There are some things like it will not be the fastest algorithm. It will take a very long time to converge. So the issue is that often these parameters can become quite big. B can be is a constant, but parameters can be quite big. So it can take a lot of time to converge. So there are also like hacks around that. So there are what are called accelerated methods where you try to get around this slowdown by by moving a little bit more than what HDD would allow you to do. But okay, that's a separate course in itself. And yeah, so that's one drawback. It can often take a very long time. And then if function is not convex, then there are other kinds of issues also. But yeah, for convex functions, convergence time is one. Something which people do research. Okay, great. Okay, so let's start about so all this was about lectures. So which at least is something about smoothness. This is a bit quite difficult, but it's kind of useful. Great. Okay. So here is the theorem for smoothness. So I will directly use the algorithm which I had earlier. I should not have erased it. Okay, because it's very again. So I just pick VD. Okay, so essentially the thing is this: you just pick VD from this, right? Some gradient of loss at WT. So sample Z from D and you pick VD from D. So yeah, that's the only change. So we'll just analyze this directly. It'll be kind of just sidestep some some calculation issues. So I'll analyze this algorithm and okay, this is what I understand. This one is so that's the algorithm. So and remember the outputs are that ratio. Okay, so with this algorithm, assuming that the loss function L is smooth, so L is beta smooth, and yeah, and convex and non-negative. You can show that if you directly prove guarantee of this type. Then expectation LD bar is at most 1 over 1 minus eta beta LD of star plus square. Okay, so that's what. So this is a slightly different kind of guarantee than last time. So, so it's when we had done. So when we analyzed regularization for smooth functions, we had gotten slightly different kind of constants here than this thing. This look a bit different. So sometimes yeah. So for some settings, those constants might actually be better. So it may be a better thing to just to just try to minimize some regularized loss instead of trying to run SGD on this. Because there's another kind of disadvantage. So sometimes you don't get the best constants. But the good thing about this is that this is easy to prove. Easier to prove than the previous thing. So let's try to at least do this. Okay, so let's prove this here now. It is this thing. Okay, so hang on. Okay, so let's try to prove it. Okay, so let's just recall some stuff about smooth functions. So there was this property of self-boundedness. It's the only thing which is crucial. So if L is smooth and convex and non-negative, then we had self-boundedness, which said that if F is is beta smooth, non-negative, and convex. Smoothness implies okay, convex. Then we had that gradient of F at W square, or is at most, I mean, is at most square root of 2 beta. So gradient cannot be very large compared to function bounded by itself. That was the thing which we proved from last time. And okay, so and then let's recall the kind of argument which we did for Lexus functions. So we had this. So let me just put some notation here to make our life a bit easier. So let me denote ft as the function which is the loss. So this is called ft of w as loss of w at zt. So zt here is the tth of example. Let's call it zt. Yeah, so maybe just PS sample. So I just call ft of w as yeah, let's abbreviate loss of w at GD, which is the thing you care about here by ft. So this is function. So for a fixed t, this is some function of w. And if you just recall the as for lectures we had, if you were trying to look at the function value, which is now this ft of w, at step t minus. Here, just want to look at this. This thing is now okay by convexity of the loss. This is at most Vt in a product. Yeah, this is true because the loss is convex, and again we have so convex loss means that ft of w star lies above the line ft of wt plus vt times w star minus vt. So you just switch it around and get this stuff. Okay, so this is very similar to the algorithm from last time, except that now since I'm analyzing this algorithm directly, I'm not writing out the entire empirical average f. I'm just talking about the loss at the direct. This is the same kind of analysis, but we're doing it more directly. Easier to do. Okay, and now we just similar tricks. Let's sum these things up. So I get that difference t of this thing, and yeah, and there's something very clean. You know what to do with this. I will just use my usual squaring tricks, and I will use this update here. So use update here to write down wt minus beta vt as wt plus 1. Then I do my cancellation, and I get that this is at most similar tricks. This is beta. So that's the last term in the telescoping which we left out, and I get these extra terms from each term of the summation. Oh yeah, all the squaring thing. So this is the same thing as that. No tricks. Okay, great. And now I want to use that it is self-bounded. Self-bounded means that all these gradients are at most this thing here. So I can bound the norm of the squared norms of these VTs. Since VT is some gradient and it is self-bounded, this is at most square of that 2 beta f of. So yeah, that's the thing, and this cancels out to this side beta outside. So I got the right. Yeah. So I haven't done anything here. I just used the previous bound for some of this type, and then use self-boundedness to bound the squares of these units. That's all. No magic tricks. Sorry. Great. Okay. Okay. So now it's just okay. Just select the right side. Now let's write down the left side. So this is just okay, so I get that summation. So I'll take this to the right. Okay. So that's the thing. That's some of our these losses for the ZDs at optimum W star. This is some of the losses of the ZDs at our WTs, and this is how much to suffer the difference. Yeah, sorry, I'm not anything. Just take it. Now I have to take expectation over my ZDs. So I have to first divide by T so that it looks a bit nicer. T. Now I want to take hang on, did I make a mistake here? Is this VF of VT? Sorry, yeah, I think I'm right. Okay. This is not a VT. Sorry, so I had gradient, right? Okay, so I had gradient. So VT was a gradient, was a gradient of WT, right? WT, not VT. VT is the answer, it's not the gradient. It's a certain WT. I'm not cheating, okay? I'm just saying that. So I had so I had VT square, right? And VT is a subgradient of the loss of the FT and WT. So this is some subgradient of the loss, subgradient of FT and WT. And then I use self-coordinates so that okay, subgradient at WT or subgradient is at most 2 beta times f of WT. I think like that. Okay, that's good. Thanks. Small mistake. Great. Now there's some stupid algebra here. I have to take this to the left side because I have this f of WT here, f of WT here. So I have 1 minus beta beta. Yeah, it's not boring. Boring stuff. Fun stuff is over. And so this now comes to the right side, and that's why I get a 1 over beta here. So now it's almost done actually. It's just a secret. Okay, yeah. So rearranging. Now finally I need to relate this back to my desired thing. So take expectation now over ZTs. ZT. Similarly here. So yeah. And by the same thing as before, expectation over ZT of this sum of these FT W stars or loss of these W's at ZT is just your true loss over distribution. This thing here is now exactly this thing here, and that thing here is now exactly. Okay. And by the way, there's one more place I have to use Jensen actually. So this is function at W's and I'm taking an average. There's one more step I need to say, okay, f of the average is at first average of the functions. That's one more step. And that completes. Okay, so yeah, so nice thing is you can guarantee like this without too much pain, without going through stability. The bad thing is that these parameters are not the best. So stability can give you better parameters. But okay, this is still useful. Okay. Yeah, I don't want to say more here. I think kind of done. I want to say more stuff in maybe some exercises and some simple things I want to say, calculations and problems. Maybe we can have a tutorial tomorrow. Yeah, same time. Okay, then your class, right? We can do earlier tomorrow. When is your class exactly? Okay, then tomorrow we will do early. Then tomorrow, yeah, I don't want to do very early actually. We can also find a different day for it. So what other day are you free in the morning? Around the same time? No day. This is the only days. Oh, I see. So it's actually tight. Okay, interesting. Okay, maybe what I'll do is in the next class I will just say a few more words at the beginning before I start the next topic. This is that. Okay, thanks.
What are we going to learn?
Okay, next time I want to do some other algorithms. So there's something called support vector machine. You might have heard the buzzword. So yeah, do that. Okay, that's the last algorithm from this topic, from this kind of optimization problem. And then I will talk about unsupervised learning.